Now we go into an example and look the possibility of using this form of first law of thermodynamics and solve some practical examples of elementary level. For example, we have a piston cylinder compressor that compresses a gas with a piston work input of 200 kilojoules. Since the gas becomes warm during this process and it loses about 45 kilojoules of energy in the form of heat that transfers out of the system from piston cylinder valves. Consider the gas as a control volume and determine its determine its change in internal energy. So what we have over here is a piston cylinder assembly that contains certain amount of mass, and during this process a work is being done on the system of the amount of 200 kilojoules, and there's amount of energy being transferred out of the system in the form of heat, and that is 45 kilojoules. Now what we need to observe is that certainly when we work on something, on some certain amount of gases, it will be going to increase its internal energy. Then if this increased internal energy loses out some energy in the form of heat to the surrounding, definitely it will be going to decrease the total increased energy by certain portion. So here we have some work being done on the system and energy being lost during the system, and if we quantify it, there's 200 kilojoules of work being done on the system and exactly 45 kilojoules of energy being lost during this process in the form of heat from the cylinder walls. So here we can see that during this process, this piston cylinder assembly this piston cylinder assembly will not going to move with certain velocity in xyz direction. No, it will not be changing its height during this process. No, so there will be no change in potential energies and no change in kinetic energies during state 1 and state 2. And because of this, we can reduce this equation by taking this second and third kinetic and potential energies respectively and replace it with 0, cancelling this term, and we now reduce this second law of thermodynamics, u2 minus u1 is equal to u plus w. Here's minus because it's been taken from the textbook, and your textbook uses certain some different approach and it depicts it takes the work done being done on the system as negative, whereas we take it as positive. So 2 answer 2 and 2 answer 2. However, we will be getting the same result. So how much energy is being lost? Minus 45, because it's being lost. And how much work being done on the system is 200. If we take it, it will be going to 155 exactly the same one as here and here. 145 and 155 and 155 kilojoules of energy difference, and it will be exactly the same difference if you consider first law of thermodynamics. It will be exactly the same difference of internal energies at state 1 u1 and internal energy at state 2 u2. Now we come to an example that an air conditioner, window air conditioner, that takes 1200 joules per second of energy from the room and pumps it out into ambience, and during this it uses about 500 joules per second of electrical energy to do it. Now, if we are using the first law of thermodynamics in the form of power, that's why you are observing these dots over the heat and work. Because here the data is in the form of what is the unit of power, and power is rate of producing the energy, the work, or moving the heat. So rate of energy dE by dt is unit of dE by dt is watt. So that's why there are these watt units instead of joules. So this AC takes 1200. This AC takes 500 joules of joules per second of energy per unit time, and use that energy to pump 1200 joules per second of energy per unit time and move it in the direction of a higher temperature gradient. So if we observe closely and apply law of conservation of energy in the form of power, we will come to know that there are two energies per unit time flowing into the system and one leaving the system. 1200 watt per second, 1200 joules per second, and 500 joules per second being flown into the system, and Q out dot is the rate of energy that is flowing out of the system. Now we will discuss the heat pump cycle and a thermal heat engine cycle in detail when we discuss second law of thermodynamics. But to solve this example using law of conservation of energy, we have enough data and enough knowledge till now that we can solve it, and just balance the energy or rate of energies flowing into the system and flowing out of the system to solve this problem. So 1200 watts plus 500 watts flowing in, and 1700 and Q out is flowing out. So if we equate in rate of energy is flowing into the system and equate it to the rate of energy going out of the system, we will come to know that about 1700 watts of joule per second, 1700 joules per second, that is watt, 1700 watts is flowing out of this AC into the ambience. So we solved this example using law of conservation of energy. Here we can see that if we convert the law of conservation of energy in the form of rates of energies flowing into and out of the system, then this dot appears, and this dot represents rate of change of energy per unit time. Dot is usually most of the time is used for d by dt. So if we have E and we take its differential with respect to time, we may denote it as E dot. Similarly, dq over dt is q dot, and dw over dt is w dot. So mostly dot represents when we take differential with respect to time. So we can convert law of conservation of energy into rates of energies, law of conservation of power as well. So there is no such thing as law of conservation of power, but we can convert law of conservation of energy in sort of power conservation for ideal systems. So this equation represents the rate of energies, and which is being developed from law of conservation of energy. Here we have three examples of work being done by the friction, work done by the spring force, work done by the gravitational force. So you have already sufficient knowledge, and you can just go through this slide and have an idea about how we calculate, how we quantify the work done by different forces. We have already discussed the conversion of work or conversion of energy into power in previous slides, and here we can see that we can transfer. What is work? Work is force into, for a linear system, force into distance. And if we take derivative of it with respect to time, and we assume that the force is constant during this, so we can take out the force out of the derivative, and d by x over dt. So the rate of change of displacement with respect to time is velocity. So if we have force into displacement as a work, so we have force into velocity as a power. So this is a trivial example, and if the force is not constant, then we cannot take out of the derivative, and we have to apply the chain rule. But just to give you an idea that the power is rate at which something or some engine or some machine can produce work, and work is a form of energy. So the rate at which a system can deliver energy or work is called power. And then we have a rotatory system where a constant force is rotating a rod of radius r, and during this process it produced a rotational displacement of d theta. We can see it in this picture, and force into the radius is torque. So if we wanna know the work being done by this force F, it is T d theta. And if we derivate it with respect to time to find out power, so we can say that the rate of change of theta with respect to time, that is angular velocity. So this is w, sorry, this is w, and this is w dot. So these are two examples of linear and rotatory systems, and we will discuss now in the coming slides that how we can quantify the work being done by the variable boundaries, like piston cylinder assembly. We compress some fluid and change its density, change its specific volume, and how much work we have to do certain compression, and vice versa. So we will discuss the work due to expanding boundaries or variable boundaries in coming slides. Here we again see that an example of energy where a car of 1100 kgs is being driven with a velocity such that it has a kinetic energy of 400 kilojoules. Find the velocity if the car is raised with a crane. How high should it be lifted in a standard gravitational field to have potential energy that equals to this kinetic energy? So now we want to know that if we this car's kinetic energy is transformed into potential energy, how high will it go? So here we will equate two energies, kinetic energies, and we will put it equal to the potential energy, and we solve it for the height that it can go using this kinetic energy. So again, this is the conversion of energy, first law of thermodynamics, and now we are using it for another problem solving that covers conversion of energies here, kinetic energy into potential energy. So it's very simple. Just have a look and try to understand it.